Our group NERO ROSSO consists of 7 members, everyone specializing in different fields in civil engineering that will help accomplish the best design for safety and cost efficiency. My name is Mohammed ALZAYED. I am the project manager of NERO ROSSO, our group. I am in charge of water and construction management.
My name is SULTAN ALKARBI, and I am the GIS lead. Also, I was in charge of the structural and geotechnical design team.
My name is ZAID ALMUJALLI. I'm the CAD lead. I'm responsible for the construction and geotechnical management.
My name is ALKANDARI. I am the CAD support and I took part in the structural and geotechnical design.
My name is RAAD ALSHARIF. I am the design lead and took part in the structural design.
My name is FAHAD HABIB. I am the CAD support and took part in the water and geotechnical management.
My name is ALOTAIBI. I am GIS support. I took part in the structural and geotechnical design.
Due to the high number of students enrolling in the university each year, San Diego State University is expanding its campus with a new residence hall. The new hall is located off Remington Drive and 55th Street. The area of the site is around 171,000 square feet and can accommodate 850 students. The building site is located on a slope which will require our group NERO ROSSO to provide a structural study and design for the foundation and the wall to show all of the solutions that can be applied to the project. Also, the group will provide a drainage system for retaining wall and a cost study for all alternative solutions that will be considered in the project.
Using the data provided from the topography plan, an elevation grid was developed to indicate the area and elevation of the cut and fill and the necessary volume of the backfill material to fill the void that will be retained by the wall. The elevation that was meant to be maintained is 426 feet above sea level. The center of the site was a parking lot with an elevation virtually close to 426 feet, represented by the yellow cells. North of the parking lot, the topography indicates that the elevation decreases gradually, reaching a minimum of 388 feet, varying from east to west, that needs a backfill, represented by the blue and green cells. South of the parking lot, the elevation increases to a maximum of 440 feet, also varying from east to west, represented by the red and orange cells, where a cut needs to be done. After looking into soil layer properties, wall acceptability to ground types, and fill material availability near site location, the group selected 3/4 of an inch crushed stone with a friction angle of 40 degrees and unit weight of 111.62 PCF. The reasons behind our selection of crushed stone is that it's well graded and predictable, stable under pressure, common as backfill material, good drainage material, meaning it allows water to filter through, and available and affordable in area of interest.
Retaining wall design will require a wall selection and calculations of safety factors. Due to the boring data and the condition of the site, structural team decided to design a king post retaining wall. In addition, the alternative study of the wall will address different type of backfill and different lengths in the piles that will be drilled into the ground. Furthermore, the group decided the scenarios of the building a concrete cast in place cantilever wall and segmental geogrid. However, based on our structural study, due to the soil having several layers, which is consistent of clay, these two walls will require a high effective cost to be built because of the extensive amount of excavation required. In addition, the group will attach several calculations and study for the soldier pile wall to show the function of the wall in the location of the building. The soldier pile retaining wall design will consist of piles that will have different lengths in different sections due to the variety of soils in the location. Also, the wall will require a design of tiebacks in each section because of the different levels on the wall and different elevations.
The structural design team has followed these codes, standards, and methods in order to design the king post tieback retaining wall. A safety factor of 2.5 has been set as a desirable retaining wall safety factor.
In order to ease the design process of the soldier pile wall, the wall was divided to 6 sections. This drawing shows sections 1 to 5, which spans 530.5 feet. Section 6, which is 17 feet long, is connected to section 5 on a 90-degree angle towards the south. A total of 79 soldier piles were used, with a 6 feet spacing between each 2 piles containing the timber lagging. This front elevation plan presents the wall height, embedment depth, and tieback locations in each section.
The design structural team has selected a W18 by 86 A992 for the entire retaining wall. The steel section that has been selected has been checked through the following criteria in order to confirm the selection.
The timber lagging has a thickness of 3 inches, height of 12 inches, and a length of 5.49 feet. The lagging plays at the flange at 3.05 inches from the web of the steel section. The bearing length is 2.5 inches. We used this timber lagging for the entire wall.
As you can see, the wall height in section 1 is 14 feet and 6 inches. The embedment depth is 22 feet and 6 inches. The structural design team has decided to not use tiebacks since the wall height is less than 15 feet. As you can see, the wall height in section 1 is 30 feet. The embedment depth is 16 feet and 8 inches. The tieback distance from the ground surface is 10 feet. The tieback angle is 15 degrees. The tieback total length is 21.76 feet. As you can see, the wall height in section 3 is 21 feet and 6 inches. The embedment depth is 12 feet. The tieback distance from the ground surface is 8 feet. The tieback angle is 25 degrees. The tieback total length is 18 feet.
As you can see, the wall height in section 4 is 38 feet. The embedment depth is 21 feet 7 inches. The tieback distance from ground surface is 10 feet. The tieback angle is 15 degrees. The tieback total length is 22.87 feet. As you can see, the wall height in section 5 is 20 feet. The embedment depth is 11.1 feet. The tieback distance from ground surface is 8 feet. The tieback angle is 25 degrees. The tieback total length is 17.9 feet.
The drainage system of the retaining wall can be described as the means of eliminating the buildup of incidental water, which infiltrates the soils behind the wall. Basically, drainage system design will be a function of the water condition on the site. Our team has researched different types of drainage materials, and we analyzed the best kind for our case. We found out that the most efficient drainage was the perforated pipe drainage, and the dimensions is 24-inch by 20 feet. Perforated pipe is used for subsurface drainage to relieve the hydrostatic pressure behind the retaining wall, to allow the water to enter through the pipe and direct the water away from a specific area. Since the backfill is crushed stone, which will allow the water to penetrate the soil to reach the perforated pipe. The water is then collected in the perforated pipe running at the base of the drain and directed away from the site toward a more suitable location. As you can see in the table, we calculated the backfill for each section. The installation of the perforated pipe is divided into 6 steps: digging the trench, cutting the slope, leveling the soil, adding gravel and landscape fabric, laying the perforated drainage pipe, completing the installation.
Since the soil conditions do not present an adequate bearing capacity to withstand loads of a 6-story residential building, deep foundations were found to be a better selection than shallow foundations. Concrete piles used in deep foundations is expected to majorly increase stability and longevity of the intended building. Soil types vary throughout the site. Therefore, the site was divided into 8 sections in respect to the boring points, locations, and data. The loads on each column was calculated using the information provided about the building intended to be constructed. Deep concrete foundations were designed in each section respectively.
Section 1 has 10 piles. The depth of each pile is 45 feet. The diameter is 1.5 foot and the safety factor is 2.5. Section 2 has 16 piles. The depth of each pile is 33.5 feet. The diameter is 1.5 foot and the safety factor is 2.5. Section 3 has 12 piles. The depth of each pile is 45 feet. The diameter is 1.5 foot, and the safety factor is 2.58. Section 4 has 21 piles. The depth of each pile is 30.5 feet. The diameter is 2 feet, and the safety factor is 3.22.
Section 5 has 6 piles. The depth of each pile is 21.5 feet. The diameter is 2 feet, and the safety factor is 2.61. Section 6 has 6 piles. The depth of each pile is 42 feet. The diameter is 1.5 foot, and the safety factor is 2.5. Section 7 has 9 piles. The depth of each pile is 45 feet. The diameter is 1.5 foot, and the safety factor is 2.53. Section 8 has 2 piles. The depth of each pile is 45 feet. The diameter is 1.5 foot, and the safety factor is 2.53.
The criteria of foundation require a minimum safety factor of 2. Our design team achieved a 2.5 safety factor in designing all 8 sections.
The cost of the wall was $5,083,000, where the tiebacks cost were $24,000 and the backfill cost was $3,043,000. The Type 2 concrete filling that was used costed $1,083,000 and the lagging cost was $110,000. The steel pile costs were $522,000 and the drainage system cost was $41,000. The cost of the foundation is $729,000, where the total cost of the concrete filling costed $643,000 and the steel cage will cost $85,000.
Building a residential project as big as the SDSU new student residence hall comes with facing vital options and decisions to be made. At first, we understood that the finished floor elevation for this project was 426 feet, and because of this, we had to do a cut and fill at the location. Moreover, the fill work was required to be at the north side of the location, where the group recommended filling that area with crushed stone. At the same time, the north side of the site required a retaining wall. Our group decided it would be best to design a king post tieback wall to retain the soil. In order to design the retaining wall, our structural team recommended dividing the north side area into sections due to having different types of soil. A drainage system is required for the release of the stormwater, where NERO ROSSO chose perforated drain pipes to be set behind the wall. Our group recommended deep foundations for this project due to the location of the building. NERO ROSSO made a visual design for the whole project also. Furthermore, the group included the cost of the soil for the filled steel beam, lagging tieback anchor, deep foundation, and the retaining wall drainage.